All right, happy Friday, Honors Algebra 2. We've got this video, and I'm going to try to make it as short and sweet as possible. Unfortunately, there's a lot that we needed to get through today, and I am not there. So in graphing rational functions, day number 2, some things to keep in mind of kind of our goals for the class period today. First is to be able to find x and y intercepts of a rational function. Secondly, to be able to determine if a rational function has a horizontal slant or no asymptotes, and then to find any asymptotes that it might have. And then finally, to sketch a graph of a rational function by hand. So starting with that, we're going to start by looking at the domain of a rational function. Basically, this is all real numbers except those that would make the denominator equal 0. So in essence, your domain of a rational function is related to its domain restrictions. It's kind of another way to kind of think about that. So as we look at that, we'll go ahead and do a few examples here about finding the domain restriction, and then using that domain restriction to write interval notation. So if you notice on number 1, our domain restriction is that x cannot equal the number 4. In other words, every other number, we're going to go from negative infinity up to 4. We can't include 4. But then we're going to go from 4 up to infinity, and basically every number except 4 is what this is saying will work. In a similar way, on number 2, we would say that x cannot equal negative 3 and x cannot equal 7. So this time you're going to kind of have this separated into a couple of intervals. You're going to say negative infinity up to negative 3, and then we're good in union with from negative 3 up to 7, and then we are good in union with from 7 up to a positive infinity. So if you notice, it kind of tells you how many breaks you've got in your interval determined by the number of different domain restrictions that you've got. Notice on number 3 that it's not factored for us. We're going to have to do some factoring first here. The numerator should be x minus 4x minus 3. The denominator should be x plus 4, x plus 5. So if you think about what your domain restrictions are here, you would say that x cannot equal negative 4 and x cannot equal negative 5. And so then for your interval notation, we would say from negative infinity up to negative 4, we are good. And union with from negative 4 up to negative 5, we're good. And union with negative 5 up to infinity. So really, domain restrictions just tell you what you can't have for your x variable. Every other real number works from negative to positive infinity. So you just use those domain restrictions to kind of put your breaks in your domain. But that would be how you'd write it in interval notation. You might have seen on Big Ideas Math where they want you to state that your domain is all real numbers except. That's kind of doing the same thing. So like on number 1, you'd say all real numbers except x equals 4. For number 2, all real numbers except negative 3 and 7, and so on. Next, let's give a more formal definition for kind of an asymptote and what that is. We've already kind of talked about asymptotes when we talked about those on Wednesday in class. Let's talk about those today, kind of maybe a little bit more kind of a refined context. So an asymptote is an imaginary boundary line. So an imaginary boundary line, which helps to show the end behavior of some graph. By end behavior, we can also consider that to be kind of the limits of a graph is another way to think about that. So not necessarily on this graph how you're going towards positive 1, towards the left and right, but also limits as far as I approach x equals 2, I'm going down to negative infinity. So not just end behavior, but limits as well as kind of what your asymptotes help to show. So let's talk about how to find those asymptotes. And you might already have kind of an idea of how to find vertical asymptotes based on our notes from the previous class period. So let's focus on the ones that maybe you were not as aware of, which are the horizontal as well as the slant asymptotes. Remember, slant, another word for that is the oblique asymptotes, or what they are also sometimes referred to as. So oblique, O-B-L-I-Q-U-E. In order to find horizontal and slant asymptotes, you must use either synthetic or long division. Really, long division is probably the preferred method for most of these types of problems. After doing the division, the non-remainder portion describes your asymptote, while the remainder portion will describe the rest of your rational function. So let's kind of talk about that. Let's kind of see what we come up with here as far as that goes. So on number 4, let's just kind of start this by looking at that one. We're going to end up doing some long division here. So if we set this one up, we're going to set x minus 4 to the outside. So again, x minus 4 is going to be what goes on the outside of our division symbol. On the inside, we're going to have the x squared minus 5x plus 6. So going through and doing that division, first thing, to get x to match up with x squared, I'm going to make that an x. That would give me x squared and a negative 4x when I distribute. Remember to subtract. You can either put it all in parentheses and then subtract. Remember, what I like to personally do is change my signs to a negative and a positive. That way, x squared minus x squared is 0. Negative 5 plus 4 is a negative 1x. And then you bring down your positive 6. So now I need to get x over here to match up with negative x. The way I can do that is to get a negative 1. So negative 1 multiplied by x is negative 1x. Negative 1 multiplied by negative 4 is positive 4. And then once again, to subtract, I go through and change my signs to where negative x plus x is 0. The same way x squared and negative x squared was 0. And then 6 minus 4 is 2. So remember, the way you write your remainder is as a plus 2 over x minus 4. So let's talk about a couple things. First thing is our asymptote. The asymptote is the non-remainder portion. In other words, this one is going to have an asymptote through the line y equals x minus 1. So when you're trying to think about what type that's going to be, you're really just kind of thinking about what type of line x minus 1 is. Is that going to be a line that's horizontal, where it's laying kind of flat across your graph, or is it going to be more slanted? And in this case, it's going to be slanted with a slope of 1 over 1, meaning that we're going up 1 over 1. So that would be our slant asymptote. The remainder portion, the remaining rational function, is this piece right here. So the 2 over x minus 4, that would be what you would then use to kind of do the rest of your calculations. Okay, let's take a look at another example. So on number 5, let's take a look here for this one. To set it up, we're going to put our 2x squared minus 3 to the outside of our division bar, and then the 2x squared minus 7x plus 6 on the inside. And so looking at this, it looks like to get 2x squared to match up with 2x squared, we just put a 1. So then when I distribute, I get 2x squared minus 3. Once again, I'm going to change my signs here. So that becomes 2x minus x squared minus 2x squared is 0. Negative 7x, I guess the plus 3, let me put that in the right spot. So the plus 3 should have actually gone over underneath the plus 6. So let me get that fixed for us here. So here's that plus 3. So really at this point, negative 7x plus 0 is negative 7x. 6 plus 3 is 9. And at this point, 2x squared can't go into negative 7x anymore. So for this one, your remainder is going to be negative 7x plus 9, that quantity over 2x squared minus 3. So taking a look at the two pieces this time, for this one, my asymptote is going to be through y equals 1. So if you think about y equals 1, this time we have a horizontal line, being that it's going through y equals 1 being just a horizontal line. And then our remaining rational function this time is this guy right here, which again, that was negative 7x plus 9 over 2x squared minus 3, I believe is what it was. Yeah. Okay. In other words, when you went to graph this one, you would graph a horizontal asymptote through y equals 1, and then you'd kind of go from there with using this function down here as being what you'd look at for the rest of your function. All right, let's take a look at one more, and if you want to try one on your own, this would be a time where you could pause the video if you'd like to and kind of try it on your own. But with x squared minus 3x minus 4, remember your denominator will always become kind of your outside the division sign. The 5x plus 6 goes underneath. And if you notice for this one, x squared doesn't go into 5x at all. It goes in there 0 times. So really that entire thing, 5x plus 6, all of that is your remainder over x squared minus 3x minus 4. So again, looking at kind of your two parts here, you still have an asymptote. It's just through y equals 0. But then your remaining rational function is actually kind of everything. Well, first off, let me make sure y equals 0, that is a horizontal asymptote for us. But then our remaining rational function this time, 5x plus 6 over x squared minus 3x minus 4. Now, looking at each of these examples, I mean, it's great that we can find asymptotes that way, but trying to do long division every single time is going to start to become very tedious. And so here's where I'd like to kind of start looking for some shortcuts. And really, in order to find those shortcuts, as we look to generalize on this next page here, what that's going to basically depend on is going to be the degree of your numerator and denominator. And so let's see. For this first one, if the degree of the numerator is equal to, or let's see, which one do we want to do for this first one? Oh, I don't think it really matters. Yeah, we'll go is the same as or is equal to. So if the degree of the numerator is equal to, replace the n with 2, that was what was messing me up. If the degree of the numerator is equal to the degree of the denominator, then notice that there is going to be an asymptote at y equals 1. Actually, let me change this. Sorry, guys. Let me make sure. I think they actually go in order what I want us to look at. So if you notice, for the number 4, our degree of our numerator was 2. Our degree of our denominator was 1. So if our degree of the numerator is greater than, here we go. Now it's making sense. So if the degree of the numerator is greater than the degree of the denominator, then there will be what's called a slant asymptote. If you notice, when it was greater, that was where we had the slant asymptote. The next one is the one I was thinking of. If the degree of the numerator is equal to or is the same as the degree of the denominator, then there will be a horizontal asymptote is the type there. And that's going to be through y equals a over b. Where notice that it says a and b are your leading coefficients. So if you look at number 5, our leading coefficients were 2 and 2, which means our asymptote is going to be through y equals 1. And 2 over 2 is 1. That's where I'm getting that from. For C, if the degree of the numerator is less than the degree of the denominator, then there's still going to be a horizontal asymptote. But this time it's going to be at y equals 0. So if you notice the degree of the numerator is less than the degree of the denominator, that would be looking at number 6, where degree of 1 for your numerator, degree of 2 for your denominator, and we ended up with an asymptote of y equals 0. So really the ones that are kind of nice are B and C, because if you notice with B and C, if your degree of the numerator is the same as the denominator, then you just get to look at the leading coefficients to determine your asymptote. For C, if the degree of the numerator is less than, then you automatically have it at y equals 0. The one that's kind of tough that you really probably need the most practice with is A, where if the degree of the numerator is greater than the degree of the denominator, then there's going to be a slant asymptote. So really this first one for option A here is the only one that requires, so the only one that actually requires you to do division. The other two really don't need division. You can kind of get those just by looking at the equation. But for A, if the degree of the numerator is greater than the denominator, that's where you need to actually do that long division like we just got done doing. Okay. So last thing we need to talk about today before we graph some of these by hand is we need to talk about what are called holes, vertical asymptotes, and roots. And so to do that, to enable to talk about that, we're going to first kind of look at this function. I'm going to go ahead and factor it here for us. So x plus 3, x minus 1 for our numerator. For denominator, x plus 3 and x plus 4. And so sitting here looking at this thing, you might already notice that the x plus 3's are going to divide out. So that's the first thing we're going to talk about, is going to be to talk about holes. And so if a factor cancels out from the numerator and denominator, it creates a hole in the graph. The way you find that hole is you set whatever factor it is that you cancel equal to 0. And then you go ahead and solve. So for this one, you'd have a hole at x equals negative 3. To find the y value of a whole, what you then need to do is you need to take negative 3 and put that in for x in this remaining equation, meaning take negative 3 minus 1 over negative 3 plus 4. So negative 3 minus 1 is negative 4. Negative 3 plus 4 is positive 1. And so our whole for this particular problem was at an x value of negative 3. And if you look, your y value is going to simplify to be a negative 4. So you'd have a whole at negative 3 comma negative 4. In some classes, we already kind of talked about what it looks like when you graph it. Notice that it's kind of like your graph just kind of keeps going, but has kind of a little spot where it kind of makes a little jump. Now, the next thing we're going to talk about, if a factor doesn't cancel and is left in the denominator, it is what is called a vertical asymptote, which oftentimes we will abbreviate VA. This comes from, again, what's left in your denominator. So looking at my denominator here, I've got x plus 4. You do the exact same thing. You said x plus 4 equal to 0. You solve. But with vertical asymptotes, we've got where x equals negative 4. So graphing that, we're going to graph that here. You can hear the announcements going on as we're working through this. And so looking at that, let me see if I can pause this recording real quick for us.
If you're interested in attending the event, please stop by room 184 anytime.
Unfortunately, I can't pause it for you guys, so I'm just going to have to keep going.
Seniors, please turn in
Hear
your
how loud the
application for the
announcements are.
Kramer 212 scholarship
But with vertical
for youth
asymptotes, notice
services.
that it's an
All
equation.
applications are due
Holes
today, and no
are
late
going to be
applications will be
kind of a
accepted.
point versus
Also, while
vertical
you're there,
asymptotes,
there are
meaning
two
an
more
equation
local
kind of like
scholarships
horizontal
that have been released today.
asymptotes.
The Joanne Wooten
The
Memorial
very last thing that
Scholarship
we need to talk
and the
about,
Henry
if a
Sally
factor
Bolton
doesn't
Memorial
cancel and is
Scholarship.
left in the
Please stop by
numerator,
Student Services and pick
it
up those
creates what's
applications if
called
you're
a
interested.
root. So if you
Also,
notice,
the
this
Mission
x minus
newspaper is
1
having a
is going to be
fundraiser
what
night at
creates
Mission
a root
Cobain
for us.
Mission.
So we're going to
We
set
want
x
to jump
minus
the
1
drive this
equal to
Saturday,
0.
February 16th from 5
And then
to
by
9
adding
p.m.
1 to each
Come out
side,
and meet some
x
great
equals
food and
positive
help
1.
support your
Now a root
newspaper staff.
is a point because it's an x-intercept.
Attention all baseball
So
players.
at 1 comma
There will be
0,
a meeting for
that's going to
anyone
be where our
interested in
root
playing
is.
baseball this spring immediately after school on Friday in room 211.
Okay.
Also,
Tell you what,
anyone interested in
I'm going to go
being
ahead and make a
manager
separate
will
video as
attend
well,
as
so there's
well.
going to be kind of 2 parts to our
Attention
notes
all
today.
students
I just
interested
don't
in
want for the
trying out for the
announcements to
Shawnee
continue to
Mission
interrupt
Room
us,
Cheer
so
Squad
this will be the
in
end
the
of video part 1.
2019-2020 school year.
Video part
There is a
2
mandatory
is going
informational
to be on
trial
Schoology
meeting in
for
the
you
Shawnee
guys.
Mission Road cafeteria
Make sure you watch
on
both
February
videos because in
27th
the
at
second
6
video that
p.m.
I'm going to make in
One
just a
parent
moment,
or guardian
that's going to be
must
where we
attend with
actually go
potential
through and
new
graph.
cheerleader
So
or yelling.
sorry for the interruption,
Please
guys. If you want to
contact
go ahead and
Coach F
click to
tomorrow
the
with
second
any
video
questions
now, this
at
would be the time to do it.
cheerleading at